Hey guys, how's it going? Can you guys hear me okay? I forgot my headset at home, so I'm doing things a little differently today. All right. Last time we talked, we were going through basically how to do a t-test, and I introduced you to the equations. And can you see my PowerPoint on the screen? Yep. Okay. So we went through the equations, and then I assigned you this little sample size 7 data set to work through. Let me get you guys bigger so I can see you. How'd you guys do on that? Did you guys finish the calculations? Give me a hands up if you finished the calculations and think you did them correctly. Logan, Chance, but we went over this yesterday, Chance. Jonathan, what about Haley?
I'm confused.
Okay, so last time on Monday, it seems like forever now, we went through the calculations for a t-test. Let me actually blow this up. Maybe you'll be able to see it a little better. We reviewed what the calculations for a t-test were, and then I gave you this little data set having to do with sheep and worms. And we didn't have time to go through it, but I was like, you know how to calculate the variance, you know how to calculate the mean, you know everything you need to know to work through it. Were you guys able to work through it? If you were, raise your hand so I can tell. Okay, so Haley did do it. Samuel, not. Blaine, not. Hannah, not. Okay, for those of you who didn't, you can put your hands down. For those of you who didn't work through it, what were you struggling with?
To be honest, I mean, just going through it, like, I just didn't feel right. I just know I can't do it right. If that sounds, I know that sounds kind of sad, but
oh my gosh, Blaine, that's so defeatist to say at the beginning, I can't do it. Okay.
like, I don't mean it like that. I just more mean like, I've tried to write it out a few times, and every time I just know, like, I mess up. I know, like, I make a mistake and then I have to restart again, and it just kept happening. So I don't know if maybe I need to do it again, or
is it the equations that are throwing you off?
Yes.
Okay, right. I suspected this might be the case. So let me share something different with you. So I'm going to attempt to share my writing pad with you guys. Let's see if this will work. All right, okay, good. So let me see if I can. All right, can you guys see my equation? Okay, so So what we have, these are the equations that were on the screen a few minutes ago. This is the calculation of the actual T statistic. So you guys already know how to calculate the mean of things. And I think it's probably this equation here that is throwing you off. So there are a couple of things that I want you guys to learn in this class. One is I want you to learn how to do specific tests, so that if anybody ever calls upon you to do a specific test in the future, you're equipped to, if you don't remember it exactly, you're going to be able to very quickly get up to speed on what that test does because you've done it in the past before. The t-test is a test that I have never run except in the context of working problems in class. I was talking to, I think it was Chance yesterday. Was it you, Chance, that we were going through this calculation? I'm like, I have to look up the equations myself because I don't remember the equations because I never run a t-test. And then I was talking to my partner last night and I said, you know, I don't remember t-tests because I don't ever actually run them as part of my normal work. They're just too simplistic a sort of test. And she's like, well, yeah, but a colleague of mine just contacted me last week or a week and a half ago. You'll remember I was on a Zoom call with him working through a t-test. And it's a technique that people in molecular biology use quite a lot to test whether or not frequencies of genes are different. And so she's like, I just ran one the other week. I'm like, yeah, I never run one except as a part of class. But that said, this equation reveals certain things. So I want you to be able to run a t-test if anybody ever calls you for help and says, hey, I need to run a t-test and I don't know how to do that. But the other thing that you should be gaining from this class is a general sense of how statistics operate and what the kind of underlying framework is for thinking about things in a statistical way. And this particular instance is especially illustrative of that. And I've never thought about this before until I was working with Chance yesterday. Thanks, Chance, for coming by because it gave me an opportunity to see something in a way that I hadn't seen it before. So this equation here is called the shared or the pooled standard deviation. Estimate. So we know from our previous studies that the standard deviation is simply the square root of the variance. So it shouldn't surprise you at all that there is a square root here, and it shouldn't surprise you all that there are estimates of the variance here. So you can ask yourself, well, what is the variance? The variance is simply the sum of the squared deviations from the mean. Oops, I made a mistake there. I put a bar on top of that, and there shouldn't be a bar on top of that. So it's the sum of the squared deviations from the mean divided by the degrees of freedom. And the degrees of freedom in this case is 1 minus the sample size. So remember that this is the sums of squares. We abbreviate this SS for sums of squares. It's the sum of the squared deviations from the mean. How does each value deviate from the mean? So when we look at this equation up here, we can decompose it into a couple of spots. Let's pay attention to this part here first. When we break this thing apart, let's just pull it down here. Let's take this first section right here. This is just basically the sample size of sample 1 minus 1 times the variance of sample 1. Well, if we look up here at the variance estimate, let's do some erasing of some things that I wrote over here. If we take this and multiply it times n minus 1, what we basically then do is we cancel n minus 1, and we do this to both sides. We cancel that out, and we're left with the sums of squares. And so this section right here is the sums of squares. It's the numerator of the variance estimate. This is the sums of squares because if you take n1 minus 1 times the variance of sample 1, the variance of sample 1 is simply the sum of the squared deviations of the mean times n minus 1. Those things cancel out, and you're left with the sum of the squared deviations from the mean. So this is the sums of squares of sample 1, which means that this is the sums of squares of sample 2. Now, what we do is we then divide that by what? Well, we divide that by n1 minus 1 plus n2 minus 1, which basically becomes n1 plus n2 minus 2. These are the two degrees of freedom, the two kinds of degrees of freedom, the degree of freedom of sample 1 and the degree of freedom of sample 2. So what we've basically done is we've combined the two sums of squares, added them together, divided that by the degrees of freedom, just like you have the degrees of freedom and variance. So this whole thing up here, let me go and erase some things once again. This whole thing that is underlined in blue is simply the sample variance for two samples combined. But even though the equation looks scary, it's nothing that we haven't seen before. You guys know what variance is. You know how to calculate sample variance. It's just that now we're taking two sample variances and we're putting them together. And the way this particular equation does it is by taking the sums of squares of one, taking the sums of squares of another, and dividing by the combined degrees of freedom. You could have just as easily have written this portion of the of that equation this way. The sums of squares from sample 1 and the sums of squares from sample 2 divided by the sample size of the two samples minus 2. And this is the same thing as and when you write it this way, it looks very much like a variance estimate because that's exactly what it is. So the pooled, the pooled sample standard deviation is 1 over n1 plus 1 over n2 times n1 minus 1 times the variance of sample 1 plus n2 minus 1 times the variance of sample 2 divided by the pooled number of degrees of freedom. So we've kind of deconstructed how this part works. And then this simply then corrects for sample size. In this case, both samples are the same size. They're both n equals 7. And so it doesn't really matter that much. But in this case, these things get weighted by their sample size. So if you had one sample that had a lot of observations and another sample that didn't have a lot of observations, multiplying this times these two fractions combined basically allows you to weight the two variances by their sample size. And so the equation shouldn't scare you. You just have to decompose it a little bit. So we know how to do all of this. So let me go and pull the PowerPoint back up. Where did the PowerPoint go? Oh, I mistakenly closed it. So we know how to do all of this stuff. Let's just take the untreated section here. We had 40 worms, 54 worms, 26 worms, 63 worms, 21 worms, 37 worms, and 39 worms. And when we add all of those up, what does that sum to? Should sum to something like 280, correct?
280 is what I have.
Yep. And we have a sample size of 7, so 280 divided by 70 divided by 7 is 40. So the mean is 40. So to get the sum of the squared deviations from the mean, we have to take the value, we have to subtract the mean from it and square that. Take the value, subtract the mean from it and square that. Value, mean squared, value, mean squared, value, mean squared, value minus the mean squared, value minus the mean squared. That's easy for this one because that one's 0. That's easy for this one because that one is 1. But we can do this for all the rest of them. Let me do that really quickly. You guys do it also if you're working along from home. Should be 196, 196, 529, 361, 9 and 1, and that all sums to 1292. So this is the sum of the squared deviations from the mean. Is that what you guys got? Okay, and then we divide that by 6 because 6 is in minus 1, and that should give us the variance estimate. Which would be 215.33 ad infinitum. If we did that for the treated version of the data, so this is 18, so this is now treated, 18, 43, 28, 50, 16, 32, and 13. We should get a mean of 28.57 And I got a variance estimate of 198.62, essentially 198.62. Run through the treated data and give me some indication when you're done with the treated data. So raise your hand or use your little response thing to show me that you've completed that. Logan's got it done. Chance has it done. Haley's got it done. Hayden, did you give me a hands up earlier? Okay, I thought I saw it. It's gone now. Oh, there it is. Okay, cool. Hannah's got it. Blaine and Samuel, let me know when you guys are done. Samuel and Blaine, did you guys finish?
Yeah, I'm looking at my sum of squares. They seem to be a little bit off. For my subtotal, I got 102. I got 1,208.52, and then I divided it by 6. Just like
If you're working things by hand and you're not carrying out all of the decimal points, then there's going to be some rounding error. And
Okay.
the larger your sample size, the more that rounding error starts to build up. So that's probably just rounding error. If you were doing this in the spreadsheet, you would probably get the same values that I'm getting.
Okay.
So, all right, yeah, that's probably close enough. And when I grade your stuff, I take that into consideration when I'm grading. If you're rounding and I work things out in a spreadsheet, there's always some room for rounding error. And what I'll usually do is I'll take whatever values you have and then I'll check them and go through and work the calculations myself as you're going through. So what I've got on the screen right now is I'm just taking these things that we've gathered, the mean, the variance, the sums of squares, the degrees of freedom, and I'm just working through the equation for the pooled variance estimate. And what you can, or the pooled standard deviation estimate, and what you can see is that right here, I've worked through the equation as it has it, but you'll see that it basically returns to me the same value that I had for the sum of square. And this returned for me essentially the same value that I had for the sums of squares here when you work through the equation. So all you're really doing is you could have just put the sums of squares up there and then divided by the degrees of freedom. I'm continuing to work through this. 1291.98. Well, let's just do 1292 because I know that that's what it is, plus 1191.714 divided by 12 is equal to 206.976167 times 2 divided by 7 equals the square root of 591.1360476. And then when I take the square root of that, I should get a pooled sample standard deviation estimate, which is 7.68999659 and a bunch of other decimals. Let me know if that's what you guys got. I'm gonna try and find. Excel spreadsheet to check my own math. 7.68999.704. Okay, yeah, pretty close.
I have a question.
Yeah, Haley.
I didn't get 1,292 for the SS. Do you mind like going back through that again?
Sure. So, did you subtract each of these things? Subtract 40 from each of these things and then square them?
Yes.
And did you get these values also?
Yes.
When you did that? 196, 529. Well, let me make sure that I did that correctly. Are you doing this on a calculator?
Okay, I'm sorry. I actually did get it. I guess I didn't realize that I got it from like finding the variances. So
Yeah, it's the numerator of the variance equation. Yep. It's the sums of squares. Yep. Which was actually the point I was trying to make by going through all of this in reality.
yeah, that's
Yeah.
fun. Thank you.
No, that's remember that back when we first embarked on this on this exercise into statistics, I told you that this equation this is the most important equation in statistics, because almost everything that you do in statistics is going to be based on the sums of squares. Whether we're talking analysis of variance, which is what we'll do right after we take the test on Monday. We'll start on analysis of variance on Wednesday. Whether it's regression, any statistical technique that you use is going to be using measures of variation. How far do the individual data points vary from the mean is something that you will see over and over and over and over again. And then we almost always divide that sums of squares by the degrees of freedom. So next Wednesday, when we start talking about ANOVA, we're going to find ourselves right back here again. So it's good that you come to the realization, oh, that 1292, that's just the numerator of the variance estimate. Better to think of it not as the numerator of the variance estimate, but to just think of it as the sums of the square deviations from the mean, the sums of squares. All right, is everybody with me? Okay, all right, good. So now we have everything that we need. We have the means, we have the pooled sample standard deviation estimate. So the T statistic is simply 40 minus 28.57 divided by 7.68999659. And when we do that math, the T statistics ends up being 1.4862. Is that what you guys got?
Dr. Kolinsky?
Yeah.
When I type in the square root of 591.136, you know, what we got above,
Yeah.
I get 24.31. I don't get 7.6 for the.
Oh, what did I do wrong? Well, wait, well, let's see. Let me do my math again. Oh, it's 59.1. I misplaced the decimal point. I was doing this on my calculator and I was just having the calculator store the digits. And when I wrote it down, I misplaced the decimal point. And then if you take the square root of 59.1, the square root of 59.1 should be 7.68. Yeah, I misplaced the decimal point. My bad. That's another thing. When I go through and grade your papers, I have to be on the lookout for stuff like that all the time also. Because if you report an incorrect standard deviation estimate, for example, and it's because you were doing this on a calculator and writing these things down by hand, and you misplace a decimal point, and as a result, you get a totally wrong standard deviation estimate, I want to grade you on, are you working through the process correctly, not necessarily did you get the exact correct answer. And so even though it ends up being a totally wrong answer, because it's due to the fact that you transcribed the answer incorrectly, doesn't mean that you should be counted off for it. And then what I have to do is, if you're using that standard deviation estimate to then calculate the standard error, to then calculate the 95% confidence interval, I have to stop at that point and I have to go through and redo all the calculations from there forward to make sure that even though your estimate of standard deviation was incorrect, you did the rest of the steps correctly and you got the numbers that you should have gotten, starting with that incorrect estimate, which was really just a transcription error. So this is a transcription error. So this is why sometimes it takes time to grade tests and grade homework assignments, is because when things go wrong, I try and figure out, okay, what went wrong at this particular step? And then I follow that incorrect thing the rest of the way through. And that sometimes is time consuming. Okay, so is that cleared up? Okay, so now we have a T statistic, and this T is going to be evaluated against a T statistic of 0.05, and in this case, 12 degrees of freedom. And so we can go to Daniel Soper's website if we want to, or we can look at this up in a T table if we want to. But I'm just going to go to Soper's website because that's the quickest and easiest thing to do. When you go to his website, you can scroll down on his list of possibilities and he'll get to the T distribution. When you get to the T distribution, you can either go to the p-value calculator for student t-test. And let me actually, I'll just share my screen as I'm doing this. Can you guys see Soper's website? So I just typed in Daniel Soper, and because my computer knows me, it's the first link that comes up. And then if I scroll down, I can go to the T statistic, T distribution. Within this, I can click on p-value calculator for student t-test, and I can put in my 12 degrees of freedom, and I can put in my observed T statistic, which is 1.48, and I can calculate the p-value for that. In this case, the p-value is 0.1646.
Why is the degrees of freedom 12?
Because you have the degrees of freedom for a test is always going to be found in the denominator degrees of freedom. So we have, since we're working with two samples here, the two samples is a sample size of 7 and another sample size of 7. And each of those gets 1 subtracted from it. So 7 plus 7 is 14 minus 2. So it's basically the degrees of freedom that is in the denominator right here of this expression. So we do that, and so that's the p-value. But we can go back a page and we can say, well, what would our T statistic had to have been in order for us to reject this? And so what we can get is a t-value calculator, student t-value calculator, and we can say, well, what is the rejection t that we have to be bigger than for 12 degrees of freedom evaluated at 0.05 alpha, and we would have to be bigger than 2.1788. And because the t that we observed is smaller than the t that is the critical value of t, we conclude that these are not different. These means are not different. Because if we said that they were different, if we concluded that they were different, we would have a 16.5% chance of making a type 1 error, and we don't want to make type 1 errors more than 5% of the time. And that's what the p-value is basically telling us. We have a 16.46% type 1 error rate. Which is bigger than 0.05. And it also tells us that it's not significant because the t value that we observe, 1.4862, is smaller than the t value that we need to surpass in order to conclude that they're different. And so once again, that also tells us the same thing. So you can do it either of the two ways.
I have a question.
Yeah, Hayden.
So I don't know why I calculated this way, but I got the same value as you for the t-test. So I did 40 minus 28.57 over the square root of 215.33 over 7 plus 198.619 over 7.
That's weird. I would have to decompose the equation once again to see why that's the case. Yeah, can you take a screenshot of that and just send it to me, and I'll muse over it over the weekend?
Mm-hmm.
Yeah, but I'm not sure why it gave you the same answer, but yeah, not sure. So you forgot to put the 1/7 plus 1/7 in front of it?
Yeah.
Okay. It might have to do with the fact that these are equal sample sizes, and so it doesn't ultimately matter. This is an equation that will work for when you have equal sample sizes or unequal sample sizes. If you had unequal sample sizes, chances are that wouldn't have worked. All right. Questions about that? All right. There is, can you guys still see my screen? After this example, there's another larger example that you can work for practice, and the results are found in the PowerPoint. I'm not going to blow time on in class doing it, but it basically shows you all of the stuff. So Hayden, you can see in this case, the sample sizes are different. You have a sample size of 42 and a sample size of 36. And my guess is if you left that out in this equation, you would get a different answer because those sample sizes are different. But something you can play around with, when you want to. My advice would be to don't do this over the weekend, because what I want you to be doing over the weekend is studying for the exam, because these two sample tests are not going to be on the exam. The exam is all about distributions, populations, 95% confidence intervals, and how you go about calculating those, and working different types of chi-square tests. And so that's what I want you to be spending your mental energies on over the weekend. But work this second example for class on Wednesday, and let me know after you've taken the test on Monday that this is that you were able to work through this correctly. Once again, the more you do these things, the more fluent you're going to become in how they get done. And how they get done is important, because in all cases you're doing things like estimating variance. So what I want to do now is probably possibly, well, depending on how you guys are doing, spend the rest of the class answering questions about the homework assignment. Before we do that, let me just tell you, at 5 o'clock today, when the homework is due, I will post a key to the homework. It's already written out. I'll post that to Moodle. So however you turn your homework in, whether it's digitally, and there's a link for that on the Moodle site now, or whether you turn that in, paper copies shoved under my door or whatever at 5 o'clock, keep a copy for yourself. So, make a photocopy of it or whatever, so that you can then look at the key that'll be posted this evening and compare that to the answers that you got, and make sure that you were doing your homework correctly, because clearly I'm not going to have your homework graded and handed back to you by Monday morning, more than likely. So that's the purpose of posting the key, so you can check your work. I will be around over the weekend and checking emails. So if you get the key and you compare it to your homework and it looks like, oh my gosh, something went terribly, terribly wrong, definitely drop me an email and we'll try and get you squared away. But hopefully what we can do right now is maybe foresee some of those questions. So at this point, what questions do you have on the homework as you've been working on it so far?
So when is the null hypothesis rejected? Is that if the observed value is greater than the critical value, or is it if it's less than the critical value?
Okay, so it depends. And so let's go back and do this. So normally, let me go back and do this. All right, you guys see my screen? Yeah. So normally the null hypothesis is something like the mean of sample 1 is equal to the mean of sample 2 is pitted against the alternative hypothesis of the mean of sample 1 is not equal to the mean of sample 2. And so in these types of tests, what you're basically saying is you reject the null hypothesis if, for example, the T statistic that you observe is greater than the T statistic that is found in the table. This is referred to as the critical T statistic. And so sometimes you see it written as T crit. The T crit is critical. And so think about it from this standpoint as mean 1 and mean 2 get bigger, as this difference gets big, then T gets big. So you're looking for an observed T that is really big relative to the T that you look up in the table. And so once again, going back to the equation helps you figure out what it is that you need to do in terms of decision making. So in most cases, you reject the null hypothesis if the statistic that you're testing is bigger than the critical value that you would look up in a table. And of course, you always have to look up the correct critical value. So you need to be looking it up at the correct alpha level, and you need to be looking it up at the correct degrees of freedom. So if you mess that part up, then you'll make an incorrect decision, not because you did anything wrong calculation-wise, you just looked up the wrong number in the table. The one place where this is different is in Shapiro-Wilkes test. The Shapiro-Wilkes test is a situation where the null hypothesis is that the distribution is not different from normal, not different from a normal distribution. And the alternative is that the distribution that you observe deviates from normal. And when we do this, we calculate the W statistic. And in this case, the observed W has to be less than the critical value of W in the table to reject the null. But this is actually, as far as I know, the only case in statistics where it's flipped this way. And so let's go back to my screen. If you go to the chi-square statistic thing here, you'll notice, you'll remember is that in the section that deals with Shapiro-Wilkes, I have underlined in red, the null hypothesis of normality is rejected if the observed value of W is less than or equal to the table's value. And so I have that underlined in red here because that deviates from kind of the normal procedure in statistics. Now, the good thing for you on the exam is you don't have to do a Shapiro-Wilkes test because Shapiro-Wilkes tests are total pain in the ass to do. So you don't have to worry about this for the test, but it's just something that you should probably have in the back of your head. As we go through and analyze data later on in the class, one of the things that we're always going to do is we're going to test for normality because that's one of the underlying assumptions of all of these parametric statistical tests. So we will be doing the Shapiro-Wilkes test in R a lot, but you don't need to worry about the decision criterion because it's always going to give you a p-value for the decision, and that's what you can use. Does that help? Yeah, okay, good. What else?
I have a question on number 4.
Number 4, what did I do? Let me find what I did with my key from yesterday. Was this Blaine? No, who was this? Blaine?
No, Sam.
Oh, Sam. Yeah, Sam. Number 4. Yeah. Mm-hmm.
So I'm basically to the point in the problem where I have all the expected numbers calculated and it's like summed up correctly. So then what's the next step of that problem?
So you have the expected values?
Correct.
So your next step is to basically calculate the chi-square statistic, right?
Okay.
So how do we calculate the chi-square statistic? Anybody in class can answer, but Samuel can also answer.
The observed by the expected squared divided by the expected.
Yes, that is exactly correct. Give me just a minute and I'm going to share my screen again. So remember that chi-square is always the observed minus the expected squared divided by the expected summed across all categories. Okay, so the chi-square is evaluated at an alpha level of 0.05, and where n is the number of categories minus 1 degrees of freedom. And so it's always this equation. But Samuel, remember in our conversation yesterday, how do the different kinds of chi-square? So we have chi-square test of homogeneity. We have chi-square goodness of fit. And we have chi-square tests of independence. In all cases, the chi-square statistic is the same, how do they vary from one another? Samuel or anyone else?
Is it how you get your the expected?
Yep, it's how you calculate the expected values. In homogeneity, you make the assumption that all observations are equally distributed across the different categories. So you just take the number of observations divided by the number of categories, and that's your expected. In the goodness of fit, you use some pre-existing distribution to determine what those expected values should be. And in a chi-square test of independence, you use the actual sample data themselves to determine what those expected values are. So Samuel, is this truck example a test of homogeneity? Is it a test of the goodness of fit, or is it test of independence?
Isn't it independence because you're working with the current data set?
It's not an independence test because you don't have two different classification schemes. So question 5 is a independence test. This is asking you about a single classification, days of the week, and it's asking you to compare what you observe to what you might expect based on the amount of traffic that is traveling. And so in this case, you're using the amount of traffic, and now I've lost track of where. You're using the amount of traffic, which is the proportion of the week's total traffic, to basically set up what the expected value is, which is why all of your expected values vary. But your expected value for Monday should have been 79.074. Is that right? Well, 79.074 is just 19.1% of the total number of trucks that come through on any given day. On Monday, actually, is the given day in this case. So you're at the point where you have the observed and you have the expected. So now you just need to calculate what the chi-square statistic is using this formula.
Okay, and I do that for I get one chi-square statistic for Monday through Sunday, correct?
Yep, it's so you sum it up across all the categories. In this case, the categories are the days of the week. Yep.
Okay, gotcha.
Yeah, so the trickiest part about doing chi-squares is the first thing you need to do is figure out, I'm given this question, this word problem, is this a chi-square test of homogeneity, of goodness of fit, or of independence? Because you need to figure that out before you can then say, oh, well, it's an independence test, so this is how I need to calculate the expected values. Is that getting you the answer you need?
Yeah, I think so.
Okay, all right. What else? So on the homework, what is question 2? Is that a test of homogeneity, goodness of fit, or independence?
Homogeneity.
Homogeneity. And this isn't just for Samuel, this can be for anybody. Question 5, I've already told you, what is that? It's the birth control versus religion question.
Independence.
Okay, Hayden, how do you know it's a test of independence?
Because it gives you the rows and the column totals.
Okay, so the better way of thinking of it, though, is it's asking you whether religious affiliation is independent of birth control option that people adopt. So whenever you have these two classifications, you're testing to see if one form of classification is independent of the other form of classification. And then how do we calculate expected values for a chi-square test of independence?
You just multiply the row total by the column total and then divide by the row and column total.
Yeah, you take the row total times the column total for that particular cell divided by the total, the grand total. Yep. Once again, just another way of calculating the expected values.
You said row total times column total divided by total?
Yep.
Correct? Okay.
Yep. So once again, at the end of the day, your expected value total should be the same as your observed total, because you're always dividing by the total number of observations that you have. Yep.
You said 4 was homogeneity, right?
No, 4 is a goodness of fit. Because what you're asking is, to what degree does the observed number of overweight trucks fit a distribution that you would expect based on the total number of trucks that are driving down the road? So you're using the column that I can't see on my paper right now because it got blurred out when I printed, but the proportion of the week's total truck traffic, that basically says, 19.1% of the trucks on the road are on Monday, 19.8% of a week's worth of traffic is traveling on Tuesday, 18.7 is traveling on Wednesday. So if there are a certain number of overweight trucks, we should expect them to be distributed proportionally to the amount of truck traffic that there is on each of those days.
And you would know that because the observed value would be greater than the table value if they're evenly distributed?
No, if they're evenly, so you're not testing even distribution. So let me just write the question down. So we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. The percentage of trucks on the road is 0.191, 0.198, 0.187, 0.180, 0.155, 0.043, 0.046. Now, if you're a truck driver, one of the things that you want to do is you want to put as much stuff on your truck as possible to drive it to wherever it's going, because you can make fewer trips. So you might expect that because weigh stations are closed on the weekends generally, you might expect more truck drivers to overload their trucks on the weekends when weigh stations are closed. So when we look at the number of trucks that are overweight, we find that there are 90, 82, 72, 70, 51, 18, and 31. And so it looks like on the weekends, the total number of overweight trucks goes down, probably because just the number of trucks that are around total has gone down. So what you do is you sum this whole thing up, and this is 414 trucks. And so what you do is you take 0.191, multiply it times 414, and that gives you the number of trucks that you would expect if the number of overweight trucks was proportional to the number of trucks on the road each day. And so that's 79.074, which is a good ways away from 90. But then when you look at the next 1.198 times 414, that ends up being 81.972, which is pretty darn close to 82. And so what you find when you do this, the conclusion that you should reach when you do this, is actually you find in this case that the chi-square test ends up being not significant because the number of trucks that are overweight is proportional to the traffic of each day. Does that make sense? All right, we are out of time. If you have other questions, I'll be around during office hours. And also, like I said, you can feel free to contact me via email. All right.
Thank you.
Talk to you guys later.